Okay, this is my Physics 2 Lab 4 magnetic field of a permanent dipole. The purpose of this field is to measure the distance dependence of the magnetic field due to a small bar magnet and compare the values computed using the Biot-Savart laws. And then my results are the distance dependence is negative 4.17 meters, and then the magnetic moment is 1.4 Armstrong meter per meter squared. And then here's the Biot-Savart law, which is basically mu naught over 4 pi. And then it's relating dl to the r value, like the distance from the current over the magnitude of the r value. And that's getting the derivative of the magnetic field. And then you integrate that to find the magnetic field. And then also using superposition, which is that Earth's magnetic field and that caused by the magnet can be added to explain the magnitude direction of the measured field. And then for a magnetic dipole, we use this formula, and we're also saying that it's weaker further away from the magnet. And then mu naught over 4 pi, and then 1 over r cubed, and then also mu dotted with the r vector or r hat, and then r hat minus the mu vector. And then here is a visual of the bar magnet saying that the field is going from north to south. And then basically this is just a method I use to set up the experiment. So basically I just downloaded a magnetometer app, made sure it was aligned with the magnetic north-south axis in order to ensure that it's perpendicular to this axis so that we can add up these components directly. And then identifying the sensor. And then for the first part, I found out the distance in which the magnetic field in the x direction was 20 mu, and then 70, 120, 170, and 220. And then I repeated this 3 times for each value. And then for part two, I'm finding out the distance when the magnetic field is 100. And then I'm recording this perpendicular y component, which is how I'm measuring the off-axis 45-degree angle. And then again, I'm just repeating those processes. And then here's my observed data you can see in this Excel sheet. And so here's all the part one values that I recorded, and then the averages, and then the ln of R and ln of Bx values that are then going to be plotted on the graph, and then the off-axis field, which is the part two values, which I'm using to find B perp, and then D, and then the B net values are over here. And then here's the graph that I made of ln of Bx versus ln of R. And since K and N are constants, B is dependent on R, and the original equation is exponential, the logarithmic graph displays a straight line. And then, so the distance dependence I determined from the graph is negative 4.1716, which you can just see from this slope right here. And then this is like the formula for the slope. And then for part two, for the calculations, the magnetic moment, here's basically how I found the magnetic moment, which is 1.4235 Armstrong per meter squared. And then I'm using this formula here, which I break up over here. And then here's my coding. So I edited this line to create a function for the magnetic field just by determining R mag and R hat, and then the magnetic field, just using the formula as described earlier. And then I'm editing these lines right here to make the arrows, just editing their axes. And then I'm repeating that for each arrow, just making the first one for one and the second one two. And then I do the same with the perpendicular arrows over here, and I made 4 of them. And then I'm editing these lines just to match my average dperp from the previous slide, and the 45 degrees just to match the math that I was doing in the previous slide. Then here's my coding results, and then B perp and D, which is giving me, and then you can kind of see like the idea of the magnetic field at each position. And then what if I hadn't oriented my experiment to compensate for magnetic north and instead laid out my meter stick at some intermediate angle with respect to Earth's magnetic field? How would this have changed my results? The values would not have been as accurate, as it would not compensate for magnetic north, as the Earth and magnets magnetic fields would not be perpendicular, and thus we could not like add them up in the way that we are. And then what if I were to stick two identical magnets together end to end and run the experiment again? How would it expect my measurements to differ? Basically, the magnetic field would double. That'd be the only difference because it's just like a secondary magnet. And that's all.